I'm an editor now. Yes.
Oh. Okay, we go to slides. Let me upload them. I will.
You're going to upload them?
Yes, I will upload them because he's lost.
Are we running it off my laptop or running it off my laptop?
Okay, just a second. I will. Okay, where is it?
Good afternoon, everyone. Welcome to the first meeting of the proposed Path-Aware Networking Research Group. We are collecting our slides. Give us a moment. I'm guessing you don't want to see the IPPM rechartering discussion. Those are the wrong slides. Where did I put those? Yep. Huh? What? Oh yeah. Where's Tommy? Oh, hey, there's Tommy. Yeah. So, can you do the minutes for this? Can I ask for a JabberScribe? Frank? Sorry, I'm just messing with you. Yeah. Okay. Can anyone do the JabberScribing? Aaron? Okay. Yeah, right. Lars doesn't have a laptop. I don't want chili on the minutes. Dave? All right. Yeah. Why did that change the boom? Aha, now we have a zooming problem. Yes.
How long does it take? After I upload them, how long does it take to see them here?
They should. Oh, there's a. We'll run it off your laptop out of the email. So we just got the first group of slides. There apparently are CDN problems, so they may not be appearing in the thing. Let's go on. Let's do this. As I said, this is the Path-Aware Networking Proposed Research Group. I'm Brian Trammell. This is Jen Linkova. We are your chairs. This is a IETF Proposed Research Group. The IETF follows the IETF Intellectual Property Rights Disclosure Rules. Please note well. So our agenda today is going to introduce what all of this is all about. We're going to have 3 presentations sort of at different points in the space of path-aware networking. The idea is really to look at these as all sort of a common theme in networking, all of which is relatively close to the IETF. And the idea is to see if we have a scope that would be interesting for founding a working group or for founding a research group around this. There should be a jar here, and I put $1 in it every time I say working group. So there's a lot of room for discussion at the end. I expect there will be quite a few questions. Why are we here? So we identified a common theme of path awareness and a whole bunch of research that's on the edge of standardization or being standardized within the IETF. So the most obvious of these is multipath transport protocols. So MPTCP is the obvious one. This is going through standardization. Quick has an item on its charter to look at multipath, though not yet, I believe, but it's definitely in scope. There's also a lot of work on hybrid access approaches. So this is where you take two access network links and you bond them together and you do things with flows over those. So you're actually doing sort of like traffic engineering to the access network. There was the banana BOF on Monday. That's an effort that's been going on for a while. There's also work on doing sort of proxying stuff and MPTCP for this. Slightly more exotic are sort of path control approaches. SFC is looking at this, and also segment routing work in Spring, so IPv6 segment routing. So the ability to actually be able to say, okay, you have to visit this router and this router and this router on the way. That's pretty explicit path control right now. That tends to work in a single administrative domain, but it looks like an enabling technology for something that might be more than that. There's work on dynamic interface and dynamic transport selection, which is another way that you can get your traffic to go down different paths or paths with different properties. So there's the multiple interfaces work in the MIFWG. That was a working group, or was that? I forget where that came from. That was from MIF. And then also some work on socket interfaces and on dynamic transport selection in the TAPS working group. And then there has been interest in path signaling, came out of the IAB Stack Evo program a year ago. Next week, the plus BOF. And then also there's the Alto working group. There's signaling about properties in the path. In that case, it's sort of something that's out of band. So all of these things kind of fit together. They're strewn across different areas in the IETF. They all have kind of a research angle to them. So it seemed to us that exploring this theme does seem like a job for a new research group. We're actually aware of other of these. Please don't feel bad if we miss your favorite path-aware working group. We can come up and talk about the scope of that as like, hey, are you aware of this? Are you aware of this? Because I think some of the information about stuff that's going on in other working groups and these could inform sort of the scope of a research group. But the point here is just basically show there's a bunch of stuff going on in this space. Path awareness, very quickly illustrated. You have a network, you have some endpoints, you have a control plane protocol. The control plane protocol tells the network how the traffic flow should go. This is routing 101. Usually here in the interdomain space, that's BGP, and there's a bunch of intradomain routing protocols as well that interact with that. The important point here is that the endpoints have really actually nothing to say about the path, right? It's like, here's my address, here's the address I'm trying to get to, put the packets on the wire. The control plane tells the forwarding plane what to do, and they end up on the other side. No selection of path properties. In multipath TCP, you actually still don't have any sort of awareness of the path beyond you might have an endpoint that has two interfaces so that it can get two different paths through two different networks, or three interfaces, so on and so forth. What we're looking at is sort of the far side of this is where you have essentially a path-aware stack, which can interact with the routers, with the forwarding plane, and actually get different paths from different endpoints to different paths through the network from the same endpoints, maybe with the same addresses, maybe with the different addresses. This actually is not something that you can just do in the network. This actually does require things to happen on the endpoints as well. I mean, you can say, okay, there's this guy up here who's never shown up in a routing area working group and is talking about path awareness. And this is not really interesting because in the control plane, all routing is path aware. Every routing decision made, everything that goes down to the forwarding plane is, okay, I have a packet that's going on this next hop in the path, so on and so forth. What we're really interested in this research group is how this extends to the edge. So we're talking about endpoint discovery of paths, endpoint explicit association of properties to paths, endpoint selection of paths. And when we see especially in work like MPTCP and other multipath transport protocols, this is happening anyway, right? So if you look at how traffic engineering is happening with segment routing, this is happening anyway. These are things where it's not just sort of a static forwarding situation as determined by the routing protocol. We should be explicit about this. I should also say that, when I talk about endpoints and edges, tunnels have endpoints and edges too, and probably one way that this will end up being implemented is you essentially have overlay networks. This is how we've always done, more exotic routing over less exotic routing. There are a bunch of underlying hard problems here. So any point in time that you essentially have a bunch of hosts connected to a bunch of networks, the host's idea of the best path and the network's idea of the best path might conflict. All right, so we're not saying, okay, well, we're going to build these overlays and suddenly, you know, BGP goes away. That's not, I think, realistic when we're talking about what's going to happen tomorrow. But already right now with MPTCP, when you have multiple interfaces that you can choose, you're actually choosing to put traffic on one path or another. And that might actually, there's a control loop that's happening at the endpoints, and that might conflict with a control loop that's happening in the network. If you're talking about scheduling at the transport layer, obviously you have more degrees of freedom when you have path awareness, right? So normally in scheduling, it's like, oh, okay, well, I'm going to use my various windows, and I know what congestion control is doing, and it's like, do I send a packet or not? And now there's a whole different degree of freedom. It's, do I send a packet or not, and which interface do I use, or which path do I use? There are temporal aspects, so all of the various bits of path selection, property discovery, any control input, all of these are happening on different timescales, and things can get very bad if those timescales happen to sync up in a bad way. There's also work to be done in the semantics of path properties. So once you have multiple paths, you'd like to be able to say things about them, like, so maybe this is a high bandwidth, high delay path, or a low bandwidth, low delay path. Right now, a lot of this is done with measurement in a path-aware network. You might actually get this information explicitly from the network. And dissemination algorithms. How do you get information about the path properties to the endpoints where they can use it? This has impacts on privacy. Obviously, what you say about a path can be used to say things about the endpoints the endpoints might not want to be said. It has also impacts on trustworthiness, the other side of that. You know, how can I trust that what you say about the path is true? So we have some text for a proposed research group charter. This is up under the charter and groups on the data tracker. I'm not going to go through this right now, but I encourage you to have a look at this, or have a look at this in the slides in the meeting materials as we're going through things, because we're going to come back to these points when we talk about whether we have the scope right or not. And this is not a BOF, but we would very much like your input on, you know, is this something that's interesting? Is this something that there's critical mass? The two big questions that I'd have are, do we have the scope right? You know, is there stuff that's missing? Are there things that we're putting in here that don't really belong in here? And then also, is there interest or energy to contribute to a new research group in this space? And if so, what should we look forward to when we're planning an agenda for Singapore? So with that, you have the slides for Olivia? Huh? They're uploaded. Okay. With that, I will ask our first speaker to come up. Do you want to just run them off of yours, or? For those of you who don't know Olivier, he's been doing things with path-aware networking for a very, very long time, even though we might not have traced it as such.
Okay, so I met Brian 1 month ago. He told me that I should try to explain a decade of path awareness, and I was foolish enough to say yes. So then let me try to show you my view. So this is a biased view based on stuff that we have done during the last 15 years or maybe more on what is path awareness, what are the issues, what are things that we tried, didn't work. It will not be a complete survey of everything that could be done with path awareness, so it's very biased, and maybe it will make up your mind so that you can have your own viewpoint of path awareness. So to look at path awareness, I think it's important to remember what are the starting point for the internet. And our starting point are very simple. So we started in the 1970s with end hosts where when people could connect to the internet, they were very happy when they managed to connect one interface of the end host to the internet. And then we had routers, and routers were basically devices with multiple interfaces. And when I teach Networking 101 and I ask a student what's the difference between a router and an end host, the answer is always an end host has one IP, has one interface and just one address. and the router has multiple interfaces and multiple addresses. And in the mind of many people, this is still the difference between end hosts and routers. What do we have today? Well, today the end hosts are slightly different. All the end hosts that we have in the room, they have multiple interfaces. They have also much more capabilities than what we had in the 1970s. So in the 1970s, when we said, well, don't put complex algorithm on the end host because they don't have enough CPU or whatever, let's put the complexity on the routers. Today, if you look at the CPU of the end host, it's very likely that the CPU of the end host that you have is much powerful than the CPU of the control plane of the routers that resides in your network, because we don't put the same CPU in the routers as the one that we put in the end host. So the environment has changed, and both the routers and the end host, they have several network interfaces, and we have to keep that in mind. So what's the interface between the end host and the network that we have today? Well, what does the end host know about the network? If you ask someone who is developing stack on an end host and you ask the developers, what do you know about the availability of the network and what's happening in the network? Basically, they know this. So from an end host viewpoint, you have very few visibility on what's happening in the network and what are the characteristics of the network that you use. For you, the network is a black box. You just send packets and you expect the packets to come back from the network, but you don't really care how the packets will flow to the network and how the packet will come back from the network. It's the same view as the view of an application developer with the file system. You don't really care about the existence of inodes and stuff like that, but you want to save your files. I think it's better to have questions after. Yeah, it's probably that many people will disagree with some of the stuff that I will say, but if we stop, I will not be able to cover everything. So what do we have? So basically, there is a tussle between what we put on the host and what we put on the routers. There is one viewpoint is that from a path viewpoint, the host is dumb and the network is intelligent. So the router has to manage the network path, and so the router needs to know what are the available paths, and it needs to have ways to be able to select the path to be used to reach a specific destination. So it has more information. The end hosts, they only need to have connectivity, so they don't care about the path. So from a routing viewpoint, the end hosts are completely dumb device, while the routers are very intelligent. If we look at reliability of the data transfer, we have the opposite. We have the intelligent host, and we have placed all the complex functions for the reliability in the transport protocols, and even the congestion control on the end host, and all the complexity is placed on the end host to have devices in the network that are as simple as possible, and they only forward packets. So we have a duality between reliability and network information. And the routers, they only queue and may drop, maybe mark packets if ECN is deployed. So what is path awareness, and how can we define that? So there are two viewpoints for path awareness. There is a control plane viewpoint, where how can a host learn the existence, the availability, the characteristics, or whatever, of different network paths that exist inside the network that it can use. And there is the data plane viewpoint, which is how, as a end host, can I tell the network which path I would like to use to reach a given destination. And there might be another question, which would be to say, whether the end host has to be aware of the paths that are used. If you want to exploit multiple paths, I will argue later on that it's better for the end host to have some visibility on the path that it uses. And at least you have to know whether you are using path A or path B, otherwise you will have issues with congestion control and mechanisms like that. So let's look at path awareness and some evolution of path awareness on the internet. So if you look at the first generation routing protocol, let's say RIP, for RIP, what was important was to have connectivity, and as long as you have one path to reach a destination, everybody is happy. And you don't want to do more than that with those kind of solutions. And if you have multiple paths in the network, what you do, you use them for failover or for recovery when there is a failure in the network. And then routers have evolved. If you look at OSPF, you have the ability to compute multiple equal cost paths to reach the same destination and to do load balancing based on a hash function. And you can introduce MPLS as well to have more control inside the network. If you look at MPLS, well, we all know that the initial motivation for MPLS almost 25 years ago was to simplify forwarding by having hardware-based forwarding. And then there was an evolution in the control plane. So in the control plane of MPLS, the first solution in the control plane with TDP and later LDP was to be able to have the same path with MPLS as the one that we would get with a standard IP routing protocol, even if you did not use IP forwarding inside the routers. And you had shortest path with LDP, and then LDP evolved to be able to provide equal cost multipath and with various issues to do the hashing correctly on top of MPLS. And then there were requirements for traffic engineering, and with the requirements for traffic engineering, we brought up RSVPT with the link to OSPF-TE or ISIS-TE, so that you have a routing protocol that distributes information about the link characteristics, and you have a signaling protocol that allows to create paths between routers along the specified link and the chosen link. And the last evolution is segment routing. And basically with segment routing, what we have is that we have eventually a closer coupling between MPLS and the routing protocol. This is something that was considered to be too complex 20 years ago. And 20 years ago, we didn't want to specify that intra-domain routing should be done with a link state routing protocol, and there should be a coupling between the link state routing protocol and the solution. So we wanted to decouple the establishment of the path from the routing protocol. And so we had LDP and RSVPT. Now everybody agrees that link state routing is a stable solution, and we can leverage link state routing in segment routing to be able to compute paths without requiring LDP and RSVPT. So basically, segment routing is a way to get rid of LDP and RSVPT and to simplify the network. If you have a network which is running MPLS with whatever variant of MPLS, what's the viewpoint that the end host has on the MPLS network? Nothing. There are some researchers who play with traceroute so that they can detect the MPLS tunnels. But besides those crazy guys, nobody is aware of the fact that MPLS is used in the network. So the network is completely black for the end host. So what have we tried on the end host to have a way to do path awareness on the end host? Maybe the first solution was IPv4 source routing. And at that time, you had Token Ring that was doing source routing, and with a way to do all path explore and to discover the paths that were available in the bridge network. In IPv4, we don't have the equivalent of the all path explorer in a Token Ring network. And there was no clear interface between the network and the end host. So the end host can encode a strict or a loose route, but there is no way from the end host to know which path will be used. In the end, it was killed by security reasons because there were too many security concerns with IPv4 source routing. Later on, integrated services came. And late 90s, we need to have quality of service, and we need to have better control on the flows that we send, and we need to reserve bandwidth in the network for specific flows. If you look at integrated services from a researcher's viewpoint, what the researchers dreamed about integrated services was a solution where the end host signals the path requirement using a signaling protocol, whatever the signaling protocol, and then you have a quality of service routing protocol which is used in the network, which, based on the requirements that are expressed by the end host, will select the path and will allow the packets to follow this specific path. What did the IETF do with this researcher's dream? Well, basically, the IETF designed RSVP protocol for the end host, which allows them to signal the path requirements, but then doing quality of service routing at that time was considered to be too complex, and it was too risky to allow paths to be forwarded along non-shortest paths. So in the end, we decided to put RSVP along the shortest path, which means that RSVP is not a protocol that allows to select a path. It's a protocol that allows to reserve resources on a path that was selected as the shortest path by the standard routing protocol, because we didn't want to add quality of service routing to the routing protocol. I should go here. We had differentiated services and type of service routing. So again, researchers' viewpoint, thanks to the mark, we could do something with a close cooperation between the routing and between the end host. This did not really happen because there is no interaction between the end host and the routers and the network. IPv6 source routing, have we done something better than IPv4? Basically, it's the same solution and unfortunately, same problem from a security viewpoint. Path awareness and multi-homing. So during the last decade, we have seen more and more devices with multiple interfaces. And when you have multiple interfaces, you can influence the selection of the path without having to mark anything in the packets or use a signaling protocol. Because the basic operation of sending the packet on your left interface or on your right interface is the way for you to control the utilization of the path in the network. So once you are multi-homed, you have more capabilities in the network. So what are the solutions that we have done? Maybe my first interaction with multi-homing was on a Spark Station 1, so it's pretty long time ago. It had multiple Ethernet interfaces, and at that time, the interaction between the network and the multi-homed end host was to run RIP on the end host to listen to the RIP messages, and thanks to the RIP messages, you had a view on which paths were available in the network. I guess today nobody is using ROD on its end host, even if it's multi-homed, but this is something that we are missing from the interaction with the network. And then we have multiple protocols. So the identifier locator separation came with shim6 and HIP. The basic idea is very simple. So you have an identifier which is stable and which is associated to the host, and there are locators that are attached to the interfaces. And from a transport viewpoint, you will interact thanks to the identifiers. And from a network viewpoint, you will send those packets inside packets with the locators. And this allows you to move packets from one locator to another. So when you move or when you are multi-home, this is a solution that works well. But this is completely opaque to the transport layer, and the transport layer doesn't see which locator, so which path has been used by the underlying networking stack. So this is nice because you don't have to change the transport layer. But the drawback of this solution is that the transport layer cannot exploit the capabilities of the underlying network stack. And there is no communication channel between the end host and the network. Lisp is another solution that was designed within the IETF. The idea, again, we have a solution where the end host will have identifiers, and those identifiers are IP addresses. And in the network, we will use locators on the border routers, and the border routers will make the decision on the path that will be used between border routers from different ASs. And again, we have a solution where the end hosts are completely blind, and the routers are in control of the solution. There have been attempts in the transport layers as well with Multipath TCP and SCTP with the CMT variant, which is equivalent from what we are discussing now. So with Multipath TCP, we have a transport level solution that allows the end host to use multiple paths. And the easiest deployment is on smartphone, for example, where you have two different interfaces, and you can use Multipath TCP on the smartphone to use the two interfaces together. And what are the solutions that we have designed within the IETF to deal with that? We had to do congestion control correctly. We had to do retransmissions, reinjections, and to be able to switch from one to another. Maybe the lesson which can be learned from the design of Multipath TCP and the design of SCTP-CMT is that the fact that the transport layer has a visibility on the paths that are used by the underlying network layer is very important, because it allows the transport layer to understand what are the characteristics of a path. So if you compare Multipath TCP with TCP over shim6, for example, they are both capable of using different paths in the network, but for Multipath TCP, the paths are explicit, which means that if one path doesn't work well, Multipath TCP will know that the path does not work well and will stop using that path, or will apply congestion control or retransmission for this path in particular. If you have a solution below that hides the availability of the different paths, then the transport protocol cannot react correctly. Last solution which is being discussed is IPv6 segment routing. So that's the marriage between segment routing and IPv6. So basically, this is the return of source routing in IPv6, hopefully by solving the security issue. So that's standard source routing operation. What does IPv6 segment routing bring? My hope is that with IPv6 segment routing, we will have a standardized way for the end host to be able to encode network paths. And at least this will be within an enterprise domain, because we know that there will be issues in using IPv6 segment routing in multiple domains. What's missing? It will be a communication channel between the end host and the network to enable it to learn the available network paths. Because the fact that you can use the paths doesn't mean that you know which paths are available. So how can we give this interaction? How can we organize this interaction? Something that we are exploring with David Lebrun for his PhD thesis in my group is that most of the communication that you do from an end host are triggered by DNS operation. And the DNS is an interaction that the end host has with the network. And so what we can do if we want to create a communication channel between the end host and the network is that we can put intelligence in the DNS resolver. And every time a host does a DNS query, the DNS resolver can provide to the host the path that it should use as a segment routing header, or the list of paths that it should use. And the client can also put additional information in the DNS request. If you want to do a kind of signaling, say, I would like a path with 5 megabits per second, you could say that in the DNS message and get the answer with a path that meets your requirements. And then you can create the path. So last point before concluding, if you try to work on path awareness, you have to be aware that there is a political layer in this problem space. You have the network operator viewpoint, and for the network operator, basically the network is like the post office. So the operator is managing the network, he invests time, money, and whatever in managing the network, and he considers that the paths that are followed by the packets are his sole responsibility. And then if you look at the end user, the viewpoint of the end user is completely different. The end user thinks that he pays for the network, and since he pays for the network, he should be able to influence the selections of the paths in the network. So from an end user viewpoint, it's like driving a car. So when you drive a car, you select the path that you want to use in the network, and you don't want to use the path which has been selected by the train manager. And that's a very difficult problem if you want to deploy a solution. So I can say that the road to path awareness won't be easy, but should be interesting. And if I had to mention 3 problems that need to be looked at when looking at path awareness, they can be summarized in 3 words: scalability, security, and I hope simplicity, because if we cannot achieve simplicity, then it will never be deployed and we will never have a solution that works correctly. Thank you.
Thank you very much. Sam, you like coming up? So Sam is going to talk very briefly about Espresso, SDN for the public internet. There's a bunch more information in the slides. Actually, here, let me plug that into. Use this one on my laptop. Which is a extremely large, although not the entire internet path-aware network, I think is the way that you can talk about it. So waiting, and there you go.
All right. Good afternoon. My name is Sam. I'm representing here for Google infrastructure. So today I'm going to talk about the way we do the SDN for the public internet. And I know this topic is pretty big, but in 10 minutes, I'll try to condense as much as possible. But you have the slides, you can go back and refer. Specifically about the questions, you can always find me after the meeting, and I'll be happy to answer as long as it passes the ACL. So these slides are not IETF or IRTF specific, so you will see more color in the slides. So as you all know, we have the biggest and baddest network, and we do that very efficiently. Let me qualify that. We do this in a very, very structured fashion. So which means we need to control the network all the way up and down to that layer, and always east to west. And we should be able to manage very efficiently all the way from the transport. If you really see the transport network, we do have very large network in terms of the transport as well. And with respect to the data centers, we do have a very, very large footprint, and we just didn't end there. We are actually building multiple regions where we have more data center presence. The reason why we do this, you could think that, okay, it is very deterministic way how we actually scale things, but given the cloud requirements, we are actually scaling at much more faster rate than what we anticipated. So if you really look at the capacity of the data centers, we are actually growing almost 10 times. And that brings a very, very interesting problem within the campus of the data centers as well. So which is also going 10 times more, right? And if that is the case, the actual northbound traffic or north to south, which is growing tremendously. So we are actually, which is pretty expensive proposition, especially the internet traffic. So how we actually do this without disrupting the network? That means we need to be able to do this without bringing down the capacity. That means we always should be able to scale up, and at some point we need to scale down to roll out the new architectures as well. So that means predictability, reliability are very, very important aspects, and I will cover those as well. So if you have seen in the recent past, we have proposed a different, the way we actually manage the network, different ways. So we started off with how we actually traffic engineer our WAN traffic, which is amongst the data centers, which we also call as B4 network, which is the reason why we do that is we need to run efficiently the WAN links so that we could optimize our utilization. And we have pretty much very deterministic way how the actual applications are utilized, and based on the class of traffic to how much of redundancy we need to build into for the services. So it is very, very efficiently run. So that was the very first when we came out with the SDN proposal to the public. And the second topic which we covered, which was also SDN managed, was the virtual network. So you may think, what exactly the virtual network we have? We do have the infrastructure to have the services run as pretty much like a cloud customer. So you take any of the internal service, whether you take YouTube or any of that sorts, they're running as a customer from the infrastructure perspective. So the same option you have when you actually talk about Google Cloud as well, which is also called as GCP. So the infrastructure is managed by the thing which we call as Andromeda, which is the infrastructure name. And the third aspect, which we talked about, the actual how we manage the data centers itself, that is the fabric. So we know every endpoint and how the traffic is actually flowing. So we actually optimize in such a way that how we actually load balance across the entire fabric. And so to go a little bit of the details, the B4, which is actually interconnecting various data centers, which actually runs at very, very high capacity. Followed by the virtual network, which is the Andromeda, which is the foundation for the Google Cloud. And the next one is the fabrics. And it is not like one day we thought, okay, we will do the SDN way. It is a progression of how we are actually evolving the network. So as you can see, 2013, which was the first time we disclosed that we use the 5th generation fabric, which is a Jupyter, but with the egress capacity of about 1.3 petabits per second. So since then, we have evolved much and we scaled much higher. I don't have the numbers to show you. But as you can see that the scale is really, really scaling. So that means we need to really scale the internet capacity, how we actually peer with the external routers, and how do we egress the traffic, which means how do you actually load balance both the incoming traffic as well as the outgoing traffic. So in order to do that, so what we have done is we have came up with certain requirements, which is how to reduce the cost. The reason the cost actually could span into multiple areas, that is operational cost, the actual equipment cost, or the OPEX, the CAPEX, or it is how we actually evolve our architecture in such a way that we could expand to the requirement, the scale requirements, which is, as I have said, which is scaling at the rate of 10x. So how do we do that? So we wanted to actually make sure that these things are going to be managed in an efficient way. And the answer for us is the SDN, because we have mastered how to actually do this. So that's where this SDN for the public internet actually came into picture. So traditionally, the way we do is when we peer, okay, for redundancy purposes, let's take, we have redundant devices which could peer. So even if one fails, you have the failover device. The main problem with that is that, going back, if in order to scale, now we are dependent on the peer-facing device, which is, let's take peering router. And it is pretty expensive because you're now running most intelligent routing applications, and it has to scale as well. And it is, per port is pretty expensive. So how do we scale, right? So what we wanted to do is we wanted to take a look at the problem and scale it down in such a way that we wanted to move the functionality away from the device so that we dumb down the device. So when we dumb down the device, what will happen is that the logic will be moved away from the device, and the device will just peer with the peering routers. And so to put it into perspective, so we have the big data centers, and which will actually support a lot of data, and which are interconnected with the B4 network, which is the WAN network or internal WAN. And these fabrics also connect to the external world through the B2 network, which is the internet WAN for us. And so from the perspective, if you look at the user's traffic, or in this case, it could be a single user, it could be cloud user, the traffic will come into the network, and we have to ensure we need to support that if it is a search request or YouTube request or so on and so forth. So we need to actually optimize the incoming traffic to redirect to the right data center or right service to front end that request, and we need to provide back the service or the data. So if you put that into context, we have to simplify the incoming thing. So that means the device, when we are trying to manage across the network, we need to have a global view. But if you really go with the dual homing model, it is pretty local view, because the peering router will have only the view what it is peering with. And the other important aspect is the scale of the routing table is pretty high, right? So it's not scalable for us. And most of the routing in this case for the peering network is that it's all about the connectivity and the shortest path. But for us, when we optimize, it is all about the service or the applications, how actually they do. So, and the fault recovery is, of course, the most important aspect of all. So if you really look at the architecture, here is how it is. So you have the external peer, which will actually be connected to our network. So in other words, instead of having a peering router, we moved this functionality back into something called peering fabric. And this peering fabric will have BGP speakers, and these will actually exchange the BGP routes with external devices. And so from there, what we do is this information is actually be available for the controller to actually program the flows. How we do that? So here is the simple architecture from pretty like 50,000 point of view, feet point of view. So if you really look at it, because we optimize from the global perspective, the end host should be able to route it to the right the peering interface. So that means all the way from the fabric or from the GFE, we need to be able to do that. So in order to do that, we need to build the intelligence, and the intelligence is actually derived based on the application performance that is fed back into the global view, which is the global controller, and that will actually feed the information back into the local controller, which is per metro or per pop, and which will enable the flows which are to be programmed, which we use the MPLS as the data plane to actually say that, okay, if I receive a request from here, the host can actually program or already have the programmed flow to egress the traffic via this particular peering interface. So this is the very simple. So what we do is instead of managing or managed by the router facing the peering sites, rather what we do is we build this logic so that we are now aware of how the traffic is originating from which peering site and how the traffic is actually egressing out of the fabric. So we could actually control this via flows, and we don't do any rocket science there. We pretty much simplified the whole thing in such a way that we could actually scale it. So if the capacity goes up, we should be able to scale the peering fabric much higher rate, and we can have many BGP speakers who can actually do that, and we shard the task across this BGP speaker so that the routing table could be constrained to whatever size we would like to. Having said that, the whole of the thing, the availability is very, very important, right? So you can actually look up the slides why we emphasize on that. And the challenges are that the reason why we do this is because we wanted to scale both network, compute, and the storage. So storage is pretty much most of us do already. Network we are trying to do, and the compute is the one which we actually scale it as well. So depending on how we actually do that, how the traffic we are dealing with, we can actually scale up and down the compute. So three together will actually provide us a better utilization of our resources serving the internet.
Great.
And with
Thank you very much.
10-minute overview of what we do.
10. Thanks a lot. So Adrian, you'd like to come up? We'll just run them off yours. Yep. Hopefully that'll be smart enough to put the thing on the right thing. There you go.
All right. Good afternoon. Going to present Scion. This is our secure internet architecture, which provides path awareness and meaningful multipath. It's actually a secure interdomain architecture, but I'm not going to talk too much about the security of Scion. I'm mainly going to talk about the path awareness and the multipath aspects and the routing itself. So our main architectural design goals were, first of all, high availability. So our goal was to be able to communicate as long as the network path exists without an adversary. So ideally, if we have a network with malicious routers, perhaps malicious ASs, we'd like to be able to communicate as long as we do have an end-to-end path without an adversary. That's a big, difficult challenge to achieve. Next, we also want to achieve secure entity authentication for a variety of entities, ASs, as well as end domains and websites and so on. And we also like for trust to be flexible so that any entity can decide whom they want to trust for their operations. We also seek transparency so that it's always obvious what's happening to our data packets or whom we need to rely upon for our operations. Then for control, we like it to be balanced across ISPs. Of course, ISPs need to have control over network paths, but we'd also like senders and receivers to have some amount of control. Not too much control, so not source routing, but some limited form of control that is meaningful to select amongst multiple paths, for instance. Finally, our goal is also to achieve scalability, efficiency, and flexibility. So I'm first going to talk about isolation domains. This is the basic principles behind Scion, which is that in order to achieve scalability, we split up autonomous systems into these isolation domains. So an isolation domain encompasses thus a set of autonomous systems. And so we see, for instance, an autonomous system here. And then we have an isolation domain core. These would be the top tier ISPs who manage an isolation domain. And here we see an example of a core AS. Then also these isolation domains are essentially virtual control planes, so they can also overlap. So one AS may be part of multiple isolation domains. So then we run actually two sets of routing protocols. We run one across isolation domains and one within each isolation domain. So next I'm going to briefly describe how routing works inside an isolation domain. So we call this process beaconing. And in essence, we have core ASs, K, L, and M that all issue routing beacons. And they, similar to today's routing updates in today's internet, they traverse the network. However, what's different is that they're only issued by the core ASs. So then these routing beacons trace their path through the network, and an AS receiving one of these beacons now has a path back to the ISD core. And so on and so forth. So each core AS sends out these beacon messages, they traverse, and a variety of paths is being learned. So now, we disseminate a number of path properties. So these beacon messages, they record path properties as they're being forwarded, and they record information such as MTU, available bandwidth, path policy, various services that are being supported, cryptographic algorithms that are being supported, and so on and so forth. So we then differentiate between up and down path segments, but in essence, it's any segment can be used in both ways. And just the way we draw it is we draw the core at the top, and so hosts or domains are at the bottom. So we call it an up path if the path is being used towards the core, and the down path for paths are being used from the core to a non-core AS. Then we also have a path server infrastructure to disseminate these paths. And essentially, each AS has one of these path servers. They offer lookups for an isolation domain and an AS number, and they return down path segments to the destination, core path segments across ISDs, and up path segments to the ISD core. So then the way this all is initiated is an AS learns multiple paths to the core. So the AS would look at their paths and inspect and see which paths they want to re-announce to their local clients. In this case, all the paths are being used. And then these paths are being registered at the local path servers. And they will be used as up paths, in this case, towards the core. Similarly, AS then also selects down paths to themselves. So this is how a receiver controls how others reach that AS. So again, in this example, we have these 4 paths. But now one of these 4 paths is not being desired to be announced. So the AS drops it, but then the other 3, it decides to announce publicly. And they're the paths that are then being uploaded and available for others for reachability for that destination. The path exploration also works across ISDs. This is actually quite similar to how BGP operates. But here you see how a update or a beacon is being sent through the network. And again, similar to the intra-ISD beaconing, the paths are being traced, and then multiple paths are being made available in this way. So now when a path lookup happens, a host contacts a RAIN server. So this is the protocol by Brian, and it's essentially the name lookup protocol that we're using in Scion. And the host requests a given domain to look up. The RAIN server then responds with an ISD, an isolation domain number, an autonomous system number, and the local address. Different than in today's internet, the local address is quite unimportant. So only the isolation domain and the AS number are important. So then the host contacts the path server infrastructure that then returns up path, a core path, and these down path segments. Now the host is then free to combine these segments in any way it wishes, as long as it takes exactly one up path, one core path, and a down path segment to form the end-to-end path. So this is when I said in the beginning that the path selection is somewhat constrained, and so it's not fully source routing in this case. So here is an example of this. When a host in R wants to communicate with a destination in S, R looks up these up path segments and the down path segments, and now some of the down paths are not being directly connected to an up path AS, and so it also obtains these core segments, and now it can combine them in various ways. So for instance, there are also shortcuts that are possible. So one of the blue paths is one of the green paths can follow this combined intersects at O, and then the packet actually just simply goes from R to O to S, so packets don't always have to go through the core. So multiple options are possible, including these dash lines, which indicate peering links. And so even though the path is not directly sent across this peering link, or the beacon, I should say, this peering link can be discovered and can be used similar to today's internet, that at most one peering link can be traversed. So as you see, multiple paths are possible in this simple example here. Also, this obviously works for the intradomain case. So here we have a host in S communicating with a destination in E prime. And again, the host fetches up paths, core paths, and down paths. And again, multiple path combinations are possible. Although they traverse some of the same ASs, at the interface between autonomous systems, different links can be used, and they're being differentiated to create multiple paths. So here's now some examples for these path combinations. So we have, just looking at the time, I think I'm way too fast, it seems like, right? Because I'm almost done. I used to give this talk, and so I always take too long. So, I figured I'll hurry up this time. So in any event, so here we have an example for an up path, core path, and down path that is simply combined in this way. And then the packets follow the blue path. What's important for Cyan is that we cryptographically protect the paths at 2 levels. So the beacon messages themselves are protected with digital signatures, which are slow and expensive to compute and verify, but they allow anyone to verify it. But then packets themselves only contain what we call hop fields, which contain the AS level path at the interface level between the ASs. So there's essentially 8 bytes per AS, and that's being protected with a very efficient message authentication code, which routers can then verify as the packet is being forwarded. Now here we see another combination without a core path. And actually in this example here, we're also crossing the peering link. So the packet actually does not go through the IST core. And what's important is that the paths are cryptographically protected in a way that different combinations are being prevented. So an adversary has to combine the paths the way we envision them to be combined, and they cannot be arbitrarily changed afterwards. Here's another example where the peering link from P to X is being used. And what's important in Cyan is that the sender has transparency of the path. So the sender sees that its packet will leave the blue isolation domain and enter the green isolation domain at this level. So you get some amount of path transparency for the sender. Here's another example of a shortcut path similar to the one I already showed earlier. So in summary, the architecture is essentially a complete redesign and resolves a number of fundamental problems of today's infrastructure. So we have path control by senders and receivers. We have also quite a rich property discovery through this beaconing mechanism, where even mechanisms like the cryptographic techniques supported can be communicated, or services being supported can be communicated in the path that then the sender can use to select the end-to-end path. We also have a rich environment of security mechanisms, such as trust routes that can be selected by each isolation domain, and a lot of transparency how different authentication mechanisms work. There's meaningful multipath, where the endpoint can actually control the different multiple paths, and also the receiver can control which path senders can use to reach it, including the ability not to announce some of the paths and get a default off behavior. So because it's a cryptographic architecture, all the forwarding information is cryptographically protected. So if you do not announce this publicly, you can be connected to the network, so meaning you can communicate with anyone on the internet. However, other entities cannot send you directly traffic. So a lot of opportunities to use this architecture. So in essence, Cyan is an isolation architecture for the control plane, but it's really a transparency architecture for the data plane. So with that, I invite you to visit our website, where we also just uploaded our book that describes the entire architecture. And the book will also be available from Springer Verlag, but a free copy is available on our website. Right.
Thank you very much. Adrian, if you could stay up, and Sam and Olivia, if you could come up too, just in case people have sort of like wider questions. So I want to thank all 3 of the speakers. I think we got a really nice sort of like, look at the spectrum of this space. Like, so, okay, so how did we get here, and what are the goals? How does this scale up on the server side? And then how can we do things in the interdomain space, sort of with the isolation architecture. So if anybody has any questions for any of the speakers about the presentations, you can come up for discussion. And if somebody has the blue sheets, please raise them up. And if you need the blue sheets, please raise your hands if they could migrate to the right space. All right. Go ahead, Dave.
Dave Plonka, Akamai. I really liked, is it Oliver, the first presenter, your overview of things. The one thing I took towards the end, you said the difference, there's this gap between what operators want to do and what the users want. The analogy used was driving cars versus, I don't remember what the other analogy was, but anyway, what it seemed to me was missing, that maybe I can offer an idea or a word that we should be using, is expectation. The gap between that is usually managed by, I think that what we should be talking about is how do we convey expectation of users so that a network could react if it thought it was in control, and also so that the user can have an expectation of what the possibilities are in the substrate that the network's offering. And for any of you guys, I was wondering, where do you think that fits here? Because you're talking about a lot of knobs that can be turned and stuff, but I don't see where we're satisfying a user expectation or collecting the part about on what time scale they expect things to react, and that sort of aspect of it.
I think there's a difficult point, which is how to formalize in some way the user expectations and how to make sure that the network provides information which is useful for the users. And we tried that with integrated services, with various stuff. We never really succeeded. But I don't have a clue. I don't have a solution to solve that. But I agree that that's the difficult problem. How can we formalize what the user wants, and how can we formalize what the network can provide and keep it simple and usable? But I don't have a clue for that.
Right. These are really excellent research questions. That's the goal of having this research group, to have a forum to discuss these aspects as well.
Andrew McGregor. Sam, is it fair to say that in a post-espresso world, Google from the outside looks like a relatively small number of extremely path-aware hosts? Some number that's less than a few thousand.
I'm sorry?
It may even be one.
Sorry, could you repeat the question?
Is it fair to say that from the outside, Google looks like a relatively small number of extremely path-aware hosts? I mean, I think that would be true, but I'm interested in what you think.
Yeah, it could be. It's pretty transparent, right? So you really don't see how exactly we do from the back end. Because if you really look at how we host the services and how they're serviced, it's pretty transparent how they actually get originated and how they get, how the front end is actually doing its job at the back end. Right?
Yeah, for sure. That part is inscrutable from the outside.
Yes.
Spencer Dawkins. Would it be okay with the chairs if I asked how many people in this room have worked on one of the failed opportunities for path-aware networking where it was named in the first presentation?
That seems like an excellent question for you to ask. Would you like to ask that question, Spencer?
So how many people in the room, and in the Jabber room probably counts too, right? How many people in the room worked on one of the failed opportunities that was listed in the first presentation?
Clarifying question on the question. Is that one hand per failed opportunity or one hand per person?
I assume that people only have two hands, so I think it's one per person.
Julius Krobach, a clarifying question. Does that include the ones that were not mentioned?
That includes the ones that were not mentioned, yes.
Yeah, I agree, yes.
We take pull requests on the slides. Okay, that's a sizable number of hands in a room of this size.
And that's actually probably a little lower than I was hoping for. I think it's especially important to pay attention to the point from the first presentation about the political aspects of what you're doing. I was at the NANOG meeting when Jeff Houston and Dave Meyer presented SHIM 6 to the operator community. It was awesome, and not in a good way. But now that we have learned from that experience also, I think that there's a research aspect to this and a explaining research aspect to this that I think are both going to matter a lot for this research group. Speaking as the transport area director, I am thrilled to see this work going forward. I could have raised my hand twice. I'm thrilled to see this work going forward, and I'm thrilled to see it going forward in the IRTF.
Right. Bob Briscoe, I just want to explain why I didn't put my hand up, even though I've worked on a number of those things.
You haven't given up yet.
No. It's because I wasn't sure in this group, from the presentations we've had, whether we're talking about awareness of what the path was or what it is. And all the presentations have been about routing, which is something static. And everything I've worked on is awareness about what the path is and how I change it when I use it and things like that.
Right.
Which is, and PMTUD and all those sort of things, which maybe is more what it was, but you know, those things change. And it's the dynamics that I don't think have come out in any of these presentations
Right.
yet. Yeah.
So that's, if I could, that's like one of the really underlying hard problems that's also really hard is the temporal aspect of this. So that the dynamicism is really difficult to engage with, I'll say. So
yeah, maybe. So there is one point when you have multiple paths. If you look at the temporal aspects, when you have a single path, the temporal aspects is when do you decide to send the next packet, and what kind of congestion control retransmission you use to send the next packet. If you have multiple paths in the network, you have another dimension to take into account, which is the fact that when you see that your temporal characteristics are not the one that you would expect, so you see losses or you see delay, you can decide to use another path. And that's an additional dimension to the problem that needs to be taken into account, and for which we don't have a real solution. We don't know exactly when we should use a different path. So if I'm having, let's say I have a multipath TCP connection, but I'm using a single path. And then I find that this path is working badly because I have many retransmission. Should I try to continue to retransmit on this path, or should I just re-establish another path and hope that with, for example, equal cost multipath, I will end up in a different part of the network and I would have different characteristics. And when you have path awareness, this becomes possible. So you have a new dimension to which you can, when you have to react to, for example, packet loss, you can react by retransmitting on the same path or on a different path, or even create a new path to be able to do the retransmission. So this opens new dimensions to the problem.
Lars, I can have a quick and a longer point. A quick point is, so Spencer, I think, actually is distracted the discussion because it's specifically not a working group forming anything, right? So therefore, I think this is totally okay, you know. And so the worry isn't, is this ready to charter, right, or anything like that? It's a research group proposal, and it has a runway. The slightly longer thing is going the same direction as Bob's, right? And I got up when Olivier first started speaking because your talk surprised me because I keep forgetting you're actually also a routing person. Because it was all about routing, and you've done multipath TCP. So when you showed me the thing, right, where the endpoint doesn't know anything about the network, that's actually not true, because the endpoint is using the path or the path, and it knows quite a bit while it's using the network. Right, when it's booting up and it hasn't sent a packet yet, it knows nothing. But in general, it actually does know quite a bit. So, but I know you know this. We don't have to go into it. But I agree with Bob. The whole set of presentations was very routing oriented, and the difficult part comes when the interaction with transport starts. Right. For example, right, if you don't want if you want the node to know something about paths that it isn't currently using, you could say, well, the network might provide that occasionally, right? Alto has been developed in sort of that direction. And then, the question is, what's the timeliness of that information, right? You can convey things like, here's the hard upper capacity of that path. That's probably okay, right? So don't slow start overshoot. It gets trickier if you want to convey load information that is, easily stale. It gets even harder when you want to convey other pieces of information, because then you as a network have an assumption what the endpoint might do. And since we're now building QUIC, which will quickly change that, right? You can't believe that everything's going to look like TCP anymore. So that's really where the hard part is. I think I agree with Bob, right? I think that's something I think is worthwhile to talk a bit more about, because when we tried to do this in the IETF, we never had the time. It was always, we need to standardize this thing, and everybody said, no, it's not ready, and it died, right?
I think the issue is that we are working at the intersection between the routing people and the transport people, and we have to make sure that the routing people can change a bit to be in the mindset of the transport people, and the transport people need to change a bit to be in the mindset of the routing people. And this won't be easy because there are not that many people who live at this interaction for the moment.
Yeah, thank you very much, Olivier. We hope to see you as well in Singapore. I will note that there's an unfortunate, it's been noted several times in my general direction, and I will note to the rest of the room that there is an unfortunate conflict with the ideas BOF. So a lot of the routing people are over there talking about identity-enabled networks. So the one bit of feedback that comes from that was even before we got this thing completely scheduled, that what do we want to do in Singapore is get more routing people in the room, more IETF routing people in the room.
Andrew McGregor again. I just wanted to note that from the point of view of routing and from the point of view of any end system in a communication and all the ASs in between, everything is a bet on the future based on the information you have about the past. And one of the things that can be communicated between entities in this kind of space is their best estimate of the uncertainty in what they think they know about the network, and perhaps even a sketch of how they expect it to evolve. And that might be quite useful because that can narrow down the range of guessing that any particular device has to do.
So I agree that everything you do is based on what you have observed in the past and the bet that you do for the future. But if you look at what's happening today, it's sometimes difficult to guess on what has been happening in the past. So let me give you an example. So we have done some experiments on a large cloud provider, and this large cloud provider, they have multiple data centers all around the world. And when you open a TCP connection from one host in one of these data centers to another, then the TCP connection will be load balanced by using equal cost multipath over multiple MPLS tunnels. And there are different MPLS tunnels. Some go over the Pacific, others go over the Atlantic. And so depending on the TCP connection that you open, which is supposed to be from a path viewpoint, you go from one host to another, you have delays that varies by tens of milliseconds. And so if you observe what's happening on a TCP connection in this type of network where you have no visibility of the paths that are used, the TCP connection that you have observed does not predict what will happen for the next TCP connection that you will use because the network is doing equal cost multipath and you don't really know where the packets will go. So it's not always easy to get information about which is valid to make a prediction for the future, depending on how the network is organized.
Yes, I agree. That was kind of my point. If the routing system that is doing that ECMP can say, hey, these paths exist and their RTTs are roughly this, and you're going to get one of them on any given TCP connection, and only one, then that's useful information for the end system. Yes.
Yeah, but we need some interface from the routing to the end system.
Yeah, totally.
Mia Kulevin, also following a little bit up on this point. So there is this tension between who can select the path, the network or the endpoint. I'm not sure if we need like very tight coordination or like a real interface, but at least we need to look at like problems that can occur if you do like decisions in both parts on like the same time scale, or like decisions that actually try to do the opposite of the other. So there might be interactions that should be considered. I'm not sure if we really need like close coordination, but that's a question to ask. And what I actually wanted to say was, first of all, thank you very much. I really enjoyed all the presentation, and I think they framed this really nicely. I'm very interested in this topic, and I just quickly jump to the last question there. Maybe the first starting point is actually collect all these problems, write them down, or these missed opportunities, I would say, and then have a document where we can talk about these things.
Thanks for the suggestion.
Hi, Colin Perkins. So in terms of the scope and the presentations, I mean, we had a bunch of presentations on the routing aspects. There's obviously the transport aspects people have mentioned. I think there's perhaps also, we tie into the measurement and probing aspects more than has been discussed. Things like happy eyeballs, things like ICE, things like path transparency to figure out which paths work for which subsets of transport protocols very much affect this, and perhaps should be discussed more.
So it may surprise you to know that I have some thoughts on that.
I'm surprised by that.
I think that there's two ways to look at that. One, we have sort of a transitional system, right? I mean, you look at something like Zion, it's further out in the future, right? But it addresses most of these things, right? There's a transition to that, and in the and what we have right now in transport is all measurement based, right? So one of the things to think about, I think, is how you take these control loops that run off of measurement that you're doing at the endpoints with no assistance from the path, and then how you get to something where you have some assistance from the path, and then how you get to something where you have assurances from the path. And then even when you have assurances from the path, there's an implicit trust then between the endpoint and the path, and maybe you might be in a situation where you're not going to trust that, right? The path has signed it and says this is authentic, but you might run into, hard problem number one, maybe you don't have the same interests. So I think that, I completely agree with you. We should pull a lot of the measurement stuff in, and I think that there's a lot of stuff that we have learned from that that can...
Yeah, I think a lot of it is perhaps best thought of as sort of pre-transport.
Yes.
And understanding what transports might work on the available set of paths.
Yep.
Hi, Tim Chan. I think this is all really interesting, and I would certainly support a research group being formed. I think in terms of things we want to do but shouldn't, someone mentioned happy eyeballs, and at the moment that RFC is undergoing an update, so it's an active thing in a working group today. So I guess the question is to what extent there's overlap there in terms of what you might be discussing here and what's actually happening in something that will ship in products next month or whenever it happens to be. I think one of the other interesting things that I've been kind of following for far too long is one of the hands that went up is multi-homing with IPv6. So there's certainly a lot in that space. I remember the multi-6 working group being formed in 2001 or something like that. So clearly there's an amount of stuff that you could do here to maybe revisit that. But again, some of that's happening in V6 Ops. We saw a great talk by Marcus Keen yesterday, I think, or earlier in the week about how you can do path selection through provisioning domains and so on. But again, to what extent would that be in the working group, and to what extent can we discuss that here? That's, I guess, the question.
Yeah, thanks, Tim, for mentioning provisional domains. Yeah, I believe it's closely related. Yeah, so I just wanted to have it. Thanks for mentioning it.
So I would like to ask everyone here who's interested in this, so this is everyone who's gone to the mic line and everyone who raised their hands and everyone who laughed at the jokes. So to the point, I'm sorry if we missed your favorite path-aware thing. Please send your favorite path-aware thing to the mailing list, panrg@ietf.org, because I think we'd certainly like to collect that on the list. That might be input to an eventual document about these things, as Miria suggested. But we really want to know what we don't know, right? And we want to, so this, in the very initial stages, I think that this research group can have a knowledge transfer and pooling sort of aspect that could be very useful. And then as we figure out what we're going to do with that, but yeah, please do say, hey, you got this wrong. You didn't mention my favorite broken thing.
Rajiv, sorry. This is interesting, but might be more useful to at least prescribe a problem with a little bit more context, right? You got the UE, the user equipment, like that was shown, the devices that consume the content. Then the other side, you have the servers that provide the content, serve the content. Are we trying to solve the problem about the path awareness from both of these points of view? Because they're very, very disparate. In Google's case, what Sam presented sort of made sense because these are the entities that are pumping the content into the network towards the user equipments, the devices that consume the content. So it's very important to select the egress path in accordance with what the criteria might be to serve that content correctly to that UE at that point of time. As we know, more than 90% of the content on the internet flows from server to the UEs, the user equipment. So is this really worth solving the problem from the UE's point of view? Well, in a way, yeah, because if they have multiple interfaces, then they got to select the right interface, which would dictate the right IP address, which then in turn would dictate what the server needs to select the path. But again, I'm scratching my head, thinking that we need to prescribe the problem with a little bit more context of what's really worth for us to tackle? Is it really the UE side? Is it really the server side where the content flows the most, where the path characteristics are a lot more important?
Is that a question or is that a comment?
Absolutely comment and a question.
Yeah.
So question is,
So
what
I think there are a lot of different sort of provision architectures for various services. I think that one thing that's missing from that vision of the world is any interactive video, which is hard, and one of the places where I'd expect path awareness gives you the biggest win. I think that there's an insight in your comment about maybe for the content delivery stuff, a lot of this is already solved. I mean, by just engineering within the network, you don't need to know a whole lot other than where the UE might be. But if the UE can assist in doing that selection in a path aware way that you get from your 85% good to your 95% good, that might be worth looking at. I think that CDNs are, like, content delivery in general is somewhat less challenging, also because we put a lot of brain power in it over the past 20 years, right? So I think there are emerging applications that will benefit from this more.
Sure.
I have a quick comment. I actually think the endpoints are also very important because the problem there is sometimes more tricky. When you're talking about servers, you're mostly thinking about how can I put more bandwidth. For endpoints, it's like wired, wireless, 3G, multi-homed hosts with different addresses. Some of them might not be usable at all. And if endpoint couldn't reach a content delivery system, doesn't matter how much effort we put into path awareness on servers.
Yeah, certainly that's true. But if the client happens to have only one interface to get to the network, all bets are off. But if the client has more than one, then I agree. Then there's a need for, again, on the server side to figure out what part, what interface, what network to which the interface is connected to might be better to serve that piece of content with whatever SL is required for that on that path.
Just one comment. Even if you have a single interface, you usually have IPv4, IPv6. And you have equal cost multipath that allows you to use multiple paths in the network. So even one interface, you might have path awareness requirements.
Yeah, I agree. And Happy Eyeball kicks in pretty well in that regard.
So we're getting close to the end of time. I'd like also, I mean, I really don't want to cut off this discussion because I'm really enjoying it. But if you have anything you'd like to say about the questions, please focus on that. Thank you.
Spencer Dawkins again. I'd like to speak in support of Miriam's suggestion to do the survey as like one of the first steps that the research group takes on. I think that there's been a real aspect of this stuff that basically it's like, ooh, I touched that, it's hot, and I'll never touch anything that looks like that again. So the ability of the people who have worked on stuff to pass on what they've learned has been really limited. I think that would have several positive impacts, but I think just collecting them would be worth it if you didn't do anything else with them. I think just for a better understanding of what we're looking at. I am really excited about what y'all are doing here, and this looked to me like one of the research groups that could easily be passing stuff over to the IETF as time goes on, because I think we're talking about stuff that people are doing today, but trying to find ways that they can do it much, much better. So it's really research, not engineering.
So Gori Fairhurst, I've often complained about people doing the same as IETF working groups, but I think this is exactly what we need to do. I think we need to have research here that attracts all the things that aren't being done in other working groups, so we have somewhere to put it. And the reason is because I think the internet has changed. That big black box is no longer the shape it used to be. Lots of things have changed, even just ECMP. So as a transport guy, I have little clue now about what's going on in the middle, and it'd be really good to know something. If the question is just, what is it I might want to know, that I think would be a really useful outcome. So I like the work.
Thank you.
Hi, Aaron Falk, Akamai. The talk on Cyan reminded me of some works I did a few years ago on a system called FARA, which was about enabling end users to use, I guess, an anachronistic metaphor, choose their own long-distance carrier in networking, which many of you probably don't know what that means, but maybe some of you. The idea is, or the point is, that I think that there's a thought that has not really come out of the discussion today, which is I feel like what we're trying to do is we're trying to enable choice. Which is has a lot of sort of economic ties, and so I think that there are other dimensions here than routing. I think if we just focus on the mechanism, we may come up with a lot of, well, we'll come up with a lot of mechanism, but I don't know if we're going to do a lot of good. So I feel like I guess I think about a lot of these problems through the Dave Clark tussle mindset. Right, we're trying to create a playing field that, to use my words, that gives the user more choice about the experience that their packets have as they're going through the network. And so I think it would be helpful to maybe put some words in the charter that talk about how are we trying to improve the experience of the internet user, right? What is this going to do that's going to be good for the internet? As opposed to, let's come up with some mechanism that allows, box A to tell box B what to do. So less of a focus on control and more of a focus on choice. But the high order bit is, I think this is great work. I hope that it be lots of people participate, and I'd love to see it happen in the IRTF.
Thank you very much.
Andrew McGregor again. One piece of scope that I haven't seen in any of the diagrams, but which I think is, if not now, that important, going to be very soon. Say I'm an enterprise. Say I want to put a large chunk of my infrastructure in the cloud, but I don't have, but not all of it. And say I realize that the biggest threat to my infrastructure when it's in the cloud is failure of my business relationship with a cloud provider. So I want to put multiple pieces of my infrastructure cloned between several different cloud providers. Now, how do I network them together, and how do I make that come out in a sane manner? And I think that is entirely in scope for here.
Marcus Keane. I'd just like to second the comments made earlier on about provisioning domains. So a lot of the initial sort of thoughts around that were to solve source selection for devices with a single interface. But there's also a clear ability to to specify sort of characteristics of each domain. Allowing talking about choice, allowing the host to choose between which path it potentially would like to take. So that's kind of it aligns kind of nicely with this.
Cool. Thank you very much.
There's one comment from the Jabber room actually. I don't know who the person is, but they said that that something about making sure people understood the IRTF versus IETF, but also I'm curious about whether the routing people would name a subset of our failed opportunities or different failed opportunities. Like, would you focus on the good stuff or lots of different ones, I guess? I don't know. Just pass that question along. Oh, and this is Allison Menken, being
Actually,
a Jabber room person for a moment.
Actually, Allison, I think this is traditionally where you come up and have your say as the IRTF chair.
Yeah, that's true too.
Yeah.
But all right. So this is the first time I've done a proposed research group, and you, as people know, or don't know, RFC is 7418 kind of has our informal approach, which is that we can have a year of proposed research group once you've gotten to this point, without actually chartering it formally. So I don't know whether Lars took hums or anything like that. We're going to have some review by some of the iStar just to give us some perspective. I heard a lot of positives here. I heard very good organization of the material. I did hear some questions about transport versus routing, and the fact that we scheduled this badly means that not on purpose, we didn't have a choice.
Yeah.
Means that we have a lot of transport people, but not routing people in the room, but we can fix that. One thing I'd like to know is, do people feel we're going to have to also, we'll have to be very careful to avoid IPv6 related conflicts, it sounds like, as well. This may turn out to be one of those groups that's extremely hard to schedule, but yay, another group. So I don't know that we need to ask a question. I think people should use the mailing list, and there's two more meetings ahead and a year of work, and then we'll see where things are. Refine the charter, do some work. Let's see where things are.
Okay, cool. Thank you very much, and thank you to the speakers and to everybody who,
Hi.
and to the participants and to all of you. And we will see you on the list, which is panrg@ietf.org.
Just a request if we can get the presentation uploaded to the material, because I wasn't able to find the first one by Olivier.
So we posted Olivier's quite late. That's up on the CDN now. So like it wasn't quite everywhere. So try again later, and if you still can't find it, mail us.
I could actually see it currently on the agenda. So you should be able to see the link to all presentations from the agenda and from meeting materials.
Yeah, blue sheets come up front. Ah, yeah. Take it to the secretariat. So just the registration desk. So, I'll see you in Singapore. We didn't get killed after the first one. That's good. Yeah. So, Allison, one of the things you could have done is you could have killed us right on the spot for being terrible.